Well, thank you very much, everyone. The next presentation is going to be by Flowserve Corporation. We have Brian White and Tyler Thomas presenting for us. And I'm not gonna introduce themselves because I have one of their bios, so it's gonna be faster if they both introduce themselves. So thank you very much for being here.
So my name is Tyler Thomas. I work for Flowserve in our Energy Advantage program. I've been in industry for just about 13 years, 10 of that being in fluid moving systems with Flowserve, focusing on hydraulic analysis, system analysis, and vibration analysis. So for the last, we'll say 3 years since Energy Advantage has really started and became a thing within Flowserve, we've kind of brought, help kind of build this system, build the process, and bring it to an actionable program. So.
Yeah, and my name is Brian White. I'll take a second to apologize to Carlos and Gary for not sending both of the bios. I just sent mine. I've been in the industry for about 10 years. Most of that with Flowserve, 2 or 3 years with a different company as well. But with the Energy Advantage program since we kind of started things up 3 years ago. So, title of our presentation is Various Approaches for Identifying Energy Efficiency Opportunities in Pumping Systems, which is a bit wordy, but we'll get into kind of what we actually do here in a minute. There's our bios real quick. Yeah, that's
also me.
Anyway, kind of take a step back here and set the stage for what this talk will be about, right? In industry, generally, we've had 3 or 4 areas of focus over the years that everyone likes to focus on. Obviously, safety being first. We want people to go home to their families after they work in plants and industrial facilities. Increase output, increase reliability, and all of this all the time maintaining your quality standards with whatever kind of product you're producing, right? In recent times, ESG, environmental, social, and governance, greenhouse gas reductions have really started to build momentum and become that 5th key focus area throughout industry, right? So, there's a lot of long-term projects. You think your carbon capture, electrification type things that a lot of end users are going after. However, those are bigger CapEx, long-term type solutions that are, coming now, but still a few years down the road before they're really implemented at scale. So what we've kind of tried to do is identify some of the more short-term levers that you can pull. One of the big things that we've come across is increasing the energy efficiency of flow loops. Talking about a flow loop, we're looking at a suction source through a pump, generally across some sort of control valve, and into a final user at your site, thinking a reactor or a tower of sorts. Instead of just looking at a pump in a system, can we look at that entire system and make sure that all of the things from where you're getting your suction all the way to the final end user in that plant are working harmoniously as efficiently as possible. In our 3-year journey here, we've kind of come across some other swim lanes as well that we're tapping into at this time. Power recovery devices, HPRTs, a lot of those, even the ones that are installed in facilities nowadays, are no longer operational. They were there, started up, and for some reason taken out of service, so we can look at those, try to get those back online. Cooling water optimization, seasonality changes, different needs in cooling water from summer to winter as the seasons change. General fleet scans with smaller industrial equipment, as well as we're kind of getting into the digital twin swim lane as well with some of the IoT devices that are coming into the industry nowadays. All of that being gathered, that those opportunities being identified, is kind of what led Flowserve to stand up this team, the Energy Advantage team. And they gave us, kind of 3 main tasks to focus on within these swim lanes, right? We improve the operational efficiency of plants, right? So we're looking at installed equipment already, generally. We can help out on the front end as well, but a lot of our focus is stuff that's already out there in the field, trying to increase that operational efficiency of your processes. Through that, obviously, reducing the electricity required to run those processes, and by default they are reducing greenhouse gas emissions associated with that. And then there's the cost side of that too, right? If it's less expensive or using less energy to power your operations, it's going to cost you less, as well as optimizing the efficiency within that flow loop. It's going to help maintenance and repair budgets as well, bring those down to return actual cost savings to our customers. Why are these opportunities here? You would think in the design phase, you want system's going to require X, you would design to X, right? Okay, well, a customer comes to an EPC and says, hey, Mr. EPC, we need X gallons per minute, Y feet of TDH with a pump. The EPC is going to say, okay, well, we want to make sure that that's going to be possible, so we're going to give you X plus 10%. And then that EPC is going to take that spec and give it to an OEM, a Flowserve, a Flowserve, a Gould's, whatever it is. And they're probably going to look at it and say, well, we need to hit this, so we're going to add 10%, 15% on that. So in the end, through a kind of a design creep, you're going to end up with a system that's generally oversized, can be 10, 20, 30%. Other things, some of these plants that are out there in industry now are quite a few years old, and they were originally designed for a certain feedstock. That improvements in the process over time reduce the amount of flow or required in that system. So you got something that's designed for 1,000 gallons per minute, only requires 650 now. You start seeing unnecessary recirculation back to your suction source in that. Those are things that we can look at to help kind of remove from your system. Inefficient means of control. We've run into many situations where a customer controls with both some sort of variable speed drive as well as a control valve, which is really unnecessary in most cases, over controlling your system, using more than you need to accomplish what you actually need there. Inefficient operation of assets. Sometimes customers will say, well, we've always run 2 pumps. That's just what we've done. Nobody's ever stopped to take a second and say, can one pump do this? Is there some way we can modify that pump so that it can handle the system requirements? We can come in and take a look at that, make those recommendations. The final thing being the maintenance. As your equipment is installed in the field over time, it's going to wear out. Your pumps clearances are going to open up. Valve plugs may wear out, and you'll see some unnecessary recirculation to the suction system, things of that nature, right? Why do these matter, right? 2 sides of the risk here. So we'll have the technical side I'll go over on this slide, and the next one we'll talk a little bit more about the commercial risk of running your systems inefficiently, right? Kind of to understand that, take a step back. Anyone who's worked around pumps will understand what the BEP is, the best efficiency point. As a general definition for anyone who doesn't know, your best efficiency point is the point at which your impeller and volute or diffuser is designed to reduce the losses, incidence losses, recirculation losses. It is important to understand that BEP is a singular point and not a range of flows and TDH combinations. So anywhere along your pump curve, shown here in pink, that you move away from that best efficiency point is by default going to be less efficient than the most efficient point, or the highest efficiency you're able to achieve. Even within the best practice, which is generally stated as 80 to 110% of BEP, even within that range, if you move back to the left on your curve there, you'll run into things like recirculation at the discharge of your pump a little bit further. You get recirculation on the suction side. Then you kind of get into some of the mechanical issues. Your bearings fail, seals fail prematurely, all the way back to your high temperature rise there at your MTF at minimum continuous thermal flow, where your pump's going to start taking on excessive heat. Possible to have alignment issues there, which obviously is going to lead to higher vibrations and premature failure of your pump. Similar issues as if you move out to the right past BEP too far, seals, bearing issues, run into cavitation as you get further out in your curve, and your NPSH required tends to increase out at that point. The other side of things there is commercial risk. In order to kind of look at this holistically, walk through kind of the typical LCC for a pumping system, LCC being the total life cycle cost of that entire system. The biggest portion of that generally is going to be the energy piece of it, up to 40% of it being what it actually costs to operate that pump, right, in terms of, the cost of electricity or the operating cost of that. Shown on the screen here is the average annual operating cost equation. As they're shown there. First is the BHP, or your brake horsepower. That's the actual horsepower required at the pump. Next we have just a conversion factor from horsepower to kilowatts, operating hours, energy cost. We take this equation, we say, what can we change realistically, right? The energy cost, that's, electricity cost that you're going to get from wherever you get your electricity. Generally, in the short term, that's not going to change. There's not much we can do to fix that unless we're talking about installing a cogen on site, which is, obviously a big long-term type project to implement. Operating hours, that's not something we can change. The conversion factor, obviously, it doesn't change. So we look at that brake horsepower part, right? We dive a little bit further into that. Breaking it down into its components, we have the Q, or the flow of the pump, the TDH, total dynamic head, specific gravity, and then in our denominator, pump efficiency, motor efficiency, and constant there. Can't change the specific gravity of your process generally in the short term. Constant's a constant, but those other four terms, right? Can we look at your system and say, what does it actually need and what is the pump producing? Are we able to reduce the Q, the flow through the pump, the TDH produced by the pump, or increase the pump and motor efficiency to actually reduce the overall energy or the overall cost? If we jump back to that equation, but the overall cost that it is to actually run your pumps in that system. Next portion of it is another significant piece, the maintenance. As we kind of mentioned, operating anything away from kind of your BEP, or the most efficient point for your pumps, is generally going to reduce your mean time between failure and cause your pumps to fail more often, and thus raising your maintenance costs. So the things that we do, making our pumps more efficient in that system, are going to extend that, reduce your overall maintenance budget, provide real savings for customers in that area. The next three I'll kind of breeze through a little bit. Pump just being the actual costs for the pumps to purchase the pumps. Operation being what is paid to someone to operate those pumps, and installation and environmental. Installation being the installation of the pumps, and environmental being the disposal of those pumps. Those all account for 32%, give or take, together, but they're not necessarily something that we're going to look at in our specific program. The last part that we do, that I do want to touch on here, is downtime, right? It says 3%, you might think 3%, no big deal. However, a lot of the applications we're going to look at are critical type applications, where if it's unspared and your pump goes down, then you are not only down, but you may have to take the whole unit offline. That may result in a loss of production, and depending on what you're creating or what you're producing, those can add up very, very quickly, and that can very easily rival the energy and maintenance portion of the total life cycle cost, depending on what application we're actually looking at. I think that's where mine ends. I'll pass it over to my buddy Tyler.
Let's try and turn on a laser pointer here, because I generally talk with my hands. And my arms aren't long enough to go both sides. So before I get into really more of the technical side of what we're doing, I want to get into a small case study here. It'll kind of prep you, prime you to understand a bit more the process on how we're going through the system analysis. So with this case study, we have a system in a refinery. This is a refinery in Midwest here in the States. These pumps run in parallel operation, and really we're limited in terms of pressure that they're producing in the system for what they thought they needed downstream, right? So pretty simple PFD here. A couple pumps take a suction, from a, I believe this was a flash drum, pushing through a temp loop, going through some exchangers, and then a bypass into a heater, and then into a reactor. So what we were looking at here is when you really plot these pumps on their curve in terms of overlaying the single and parallel curve into operating hours, you can really tell that from a flow standpoint, it's almost there. We're almost there from a single pump being able to handle this. So where they were actually operating at on their parallel curve was mostly just a function of pressure they thought they needed in the system, right? So what can we do about that? The analysis looks like going and looking at that complete system, figuring out the conditions of service of what the customer needs downstream. The downstream needs past the main control valves, right? So if we have main controls basically at this temperature loop, what's happening downstream of that in terms of flow and pressure, what's needed. So if we can identify those, we can work our way back to the pump and actually figure out what's needed in that pump to go past that control valve. And many times when we're talking about design creep, there's excess pressure in the system. That's one of the main factors of finding excess energy in the system is excess pressure. So if you have a control valve that's breaking down 100, 200 psi of pressure, why is it doing that, especially at max flow rates where your differential pressure is at its least, right? So if you can find that and you can reduce it, not the downstream side, but the upstream side. And we're talking about things you can control in the pump, the TDH of the pump. That's what's putting the energy in the system, okay? So how can we look at this? What we found was there was some excess pressure in the system across those control valves. There was also a little bit of recirc that was happening in the system. So leaning on our company's expertise on pumps and valves and how to re-rate them and how to optimize them based on conditions of service, we found that we could make some hydraulic changes to the pumps, specifically the impellers and the geometry of those impellers and how they interact with the casing. So these are BB3 multi-stage pumps, so Volute style. I think these are like 11-stage pumps, so a pretty decent sized pump, and we'll call it a heritage pump. So this is an older pump, not in production anymore, has been kind of taken underneath our umbrella, right? So able to look at those hydraulics, manipulate them a bit, get them to the point where we could reduce some pressure, so which landed somewhere between the parallel or the single pump curve and the parallel pump curve. Match that hydraulic to their conditions of service, provide an optimized solution to get them to a single pump operation. So this is important because it adds redundancy to the system. Brian was talking a minute ago about we'll call it system reliability, where if you have no spares, if you're reliant on two pumps, you're stuck. If a seal goes down, just a small thing, the weak link usually, if a seal goes down, you're taking a loss of production in the system, right? So that's their focus was, hey, get us away from an instance where we could lose production, get us to a place where we have redundancy. So that's what this case study was focused on. So let's look at how the analysis actually happened. So most of the time we're dealing with brownfield situations. So these are pumps that are installed, refineries that are lots of years old, right? I think one of the newest refineries in North America is MPC Garyville, and it's old and of itself, right? So these are generally older refiners. Generally, re-rates happen at the pump. There's a request that comes in, we need a new flow and a new TDH. What we're doing here is starting at the other end. So we're looking at this control valve and we're saying, hey, what is the downstream pressure? What's needed downstream here? So this blue plot. And what do we have upstream? So this would be, our orange would be our inlet pressure into the valve, our blue would be our outlet pressure coming out of the valve. What is the difference in them? Specifically, as I mentioned, at max flow rates, where where your differential pressure is at its least. Can we bring those together, provide adequate margin for pump degradation, fouling in the system, things like that? But this reduction that we can make, which is signified by the green, what does that look like and how can we achieve it? That's step one. Figure out the downstream conditions of service. Very important. We also look at the valve, look at the controllability of the valve, make sure that if we make a reduction in pressure, generally if you see a reduction in pressure on the upstream side of a valve, you'll open that valve more to provide the same pressure downstream. Can we open it more and still maintain controllability? Are we touching, getting up into the 90% open range, 100% open range, where the valve becomes has less ability to control? And so then we look at recirculation. Is there excess flow in the system? Can we remove that excess flow? Why is it recirculating? Are you doing it to protect the pump? Are you doing it because it's a hot service and you're protecting the recirc line so you don't shock it with 700-800 degree fluid when you need to recirculate? All of these things work themselves back into a new condition of service for an optimized system that we can implement in the pump and do that re-rate. These re-rates aren't anything that haven't been seen in industry before. We've been doing pump re-rates for decades and decades and decades, and Flowserve has been doing pump re-rates for all of those decades, right? So these aren't magical upgrades. These are trims, D-stages, donor hydraulics, engineered drop-ins, things like that. Things we do on a daily basis, but are just focused on an energy optimization into the system. So I know I'm pressed for time. I'm going to start smoking through these a little bit. So the assessment process, really, we have this broken down into steps. So we're collecting assessment information. We're getting a candidacy review. So we're pulling lots of drawings, tracing P&IDs, finding out if, number one, we can analyze the system, if it has adequate instrumentation, because we really need 2 to 3 years worth of data at pretty granular intervals to catch highs, lows, max flows specifically, but we need the lows, and we definitely need the averages. That's where we're doing most of our calculations for energy savings, right? So that P&ID review and the feasibility review are pretty heavy-handed. Then we get into the system analysis and the modeling. We've developed some internal proprietary tooling to help us model those things. Then we have a really big touch point with the end user with the conditions of service overview, where we're saying, hey, this is what we're seeing so far. We have these kinds of reductions. This is kind of what we plan on doing with this pump. How does that look? What is that? Are we on the right path to get you to where you're trying to go? And then into the solution development and deliverance of the final report. I think we're done. I'm getting to Will, so we gotta keep going. And I think this is kind of saying what we just said a minute ago. It's just really these projects, we're looking at 10 to 15 flow loops. Really, that's about a 3-month time frame of the complete project. Again, with kind of the deliverance of a final loop specific report for each flow loop. That was a lot, and I went fast at the end, and I apologize, but we'll be around. We have a booth. Me and Brian will be around from the engineering side. We have a couple BD guys, so pull us aside if you have any questions. I'm more than happy to talk to you. Also have cards. You can reach out to us. Any questions?
Can you give us an idea of the order of magnitude of savings in a typical large petrochemical plant? Are we talking tens of thousands or hundreds of thousands of dollars?
Generally, we're talking hundreds of thousands of dollars. By and large, on the projects that we've completed, and we've completed, probably 20 or so in EMA, probably the same number in North America. Generally, we're finding about 20% energy reduction for any flow loop that we touch. And we're finding, in some cases, hundreds of thousands of dollars, in some cases, millions of dollars saved annually with a general ROI of 2 years, sometimes sub 2 years. What we're finding, and this really ties into the electrical infrastructure and what kind of strain that is on it right now, that many utility companies are offering incentives based on their final end users reducing their power consumption. Mm-hmm. For instance, Puget Sound Energy in the Pacific Northwest, they offer incentives that are on the magnitude of 75 cents per kilowatt hour reduced, that they'll help fund projects. So we're finding ROIs and IRRs IRRs getting up into the 70% 20-year IRRs with first-year implementation, and ROIs becoming sub 1 year sometimes. The only reason they push out past is because the end user has to make that capital spend, then they get reimbursed for it. There's a lot of energy savings. Thank you.
Any more questions? Two more questions.
Hi, Kirtan Trivedi with
you talking about in greenfield, like a greenfield project?
Yeah.
So difficult, right? So if we could get ahead, the thing is, we're not an EPC and we don't function as one. Flowserve in general doesn't function that way. It's as he mentioned, junk in, junk out, right? So if we get good process conditions and we can do away with the design creep that Brian was alluding to, then we can do great with it, right? I can specify a pump if I know downstream conditions. I know lengths of run of pipe, I know pipe diameter, I know exchange or data sheet information where I can understand the pressure drops across all those things. I can design a pump and provide a pump to you that operates at BUP with little to no loss across it. So it depends.
It's very dependent on the information we get up front, right? I mean, it's not to say that we can't be involved in that upfront process, and obviously Flowserve as a whole can certainly be involved in that process, but if it's got 30% built in already, then it ties our hands a little bit.
Okay, I'm the chairman, but I get to ask a question too. I've been dying to ask you professionals. Variable speed drives.
Yes.
I've used them a couple of times. I just love them compared to the
Same.
other system. What are the downsides, except for initial cost? Why aren't they in every system?
Cost is a huge one. I mean, if especially when you get into larger equipment, right? It's not just putting the drive there. It's a lot of times it's that whole clean room or HVAC, climate controlled room that is being put in. It's different electrical infrastructure. Anything above maybe 200 horsepower is just going to be a massive cost up front. Ideally, we would love to see every system we touch have that on it and say, okay, we'll open your control valve all the way, bring your speed down to control with your flow and head. However,
and what you're seeing these days with multiple pump manufacturers, Flowserve included, a lot of pump manufacturers are coming out with smaller VFD drives, backpack type drives that are installed directly motor mount that are considered smart pumps, taking information directly from the system, tying into that VFD, controlling that. That's starting to become prevalent. That's one of the spaces that we're looking at, one of the swim lanes, especially in chem and petrochem, where you're dealing with not a whole, like a smaller amount of high horsepower pumps, but just an amazing amount of low horsepower, averaging 15, 20 horsepower across the site. And most of those pumps being ANSI style pumps that are, you can remove them and replace them with something like a sealless pump with a VFD where you're removing horsepower that's being consumed by the seal, you're removing horsepower that's being consumed by control valves and everything. So that is becoming more prevalent and starting to come onto the scene. We're getting into that swim lane and kind of getting some initial projects off the ground. Pretty excited about it.
Angel Lanza with ExxonMobil. Thank you for the presentation. I'm curious to know how you interface with the customer. So, do you provide a free quotation for the analysis and the economics, and then after that, if the customer decides to move forward, then is when we engage differently with a payment, or you also charge a fee for the study at the front?
Multiple ways, right? So the consultation and us actually getting a business case together for you is pretty easy. In fact, we have some tools. If you go to flowserve.com and you find the Energy Advantage, we have a calculator there where you can put in some of the parameters of your site, barrel production or overall production, average horsepower of your pumps, and you can start building that business case out for yourself. But we also have 2 business development guys here in North America, both of them at our booth right now, that are more than happy to help build that business case for you, show you what we think that you can do based on things that we've done in the past. Generally, we like, I'll just be honest with you, it's hard to go and do an analysis that's 12 months long over 20 different flow loops without the end user having some skin in the game, right? We want you to be interested in it as we are interested in it. There's many times that we do it on a case where there's different contractual type obligations to say, hey, we're going to do this, but we're expecting you to make some moves with us when we provide recommendations that hit your specified target. Right? So there's a lot of different conversations you can have around this.
How good is the application for those credits that you were talking about?
Sorry. For the application for those credits that you were talking about, does your company help to apply for those?
Yeah, that's one of the things that is in our purview when we're building that case to show the end user what we think is out there. We go and look at who your utility provider is, what their incentive base is. Depending on where you're at, it really depends. I'll just I threw the gold nugget out there that happens with PCS sound to 75 cents a kilowatt hour. That is not something that is everywhere. When you get further, closer to our region here, it goes down, but it's still available. But yes, we help in that discussion. It's more than happened. We've already done a lot of research on it.
We need to move into the next presentation. So, thank you very much.